Last time we talked about the derivative of inverse tangent. That is an inverse function, also called arctangent. Inverse tangent and arctangent are the exact same function. They are different notation for the exact same function. The inverse function of the tangent function, when you restrict its domain to that first spot between negative pi over 2 and positive pi over 2. We derived, using the chain rule last time, that this derivative is 1 over 1 plus x squared. That is something that you should memorize for the gateway exam. Very important derivative. Mostly because, I mentioned this last week, in Calc 2, we need to sometimes integrate 1 over 1 plus x squared, meaning find its antiderivative. And the answer is going to be inverse tangent of x plus an arbitrary constant c for antiderivative. That's actually a more important application of this fact. But to know that fact, you have to know this fact. Today, we'll derive the derivative of inverse sine, but before we do that, let's do a little easier one, as I had you do in the participation. Let's derive the derivative of natural log of x. Natural log of x is an inverse function. It's an inverse function of e to the x. We know that e to the natural log of x equals x for all x in the domain of the natural log function. E to the x and natural log of x kind of cancel each other out. That's what it means to be inverse functions when you compose them. When you plug natural log of x into e to the x like this, you get x back. That's how natural log of x is defined. We differentiate both sides of this with respect to x, assuming, without proof, that everything's differentiable. Now, we certainly know x is differentiable. It's got a derivative equal to 1 for all x. We certainly know e to the x is differentiable for all x. I'm going to implicitly assume natural log of x is differentiable in doing this calculation, even though I really don't know that for sure, even though I haven't proved that. And again, this is true over the domain of natural log if x is positive. Differentiate both sides. This is a composition. ln of x is the inside function. E to the x is the outside. Always say this kind of thing in your mind as you use the chain rule. I need to take the derivative of the outside function, which is e to the x in this case. So you start writing e to the x, but then don't go too fast. Plug in the inside function into that. Replace x, in this case, with natural log of x. Then multiply times the derivative of that inside function, d dx of natural log of x, which I'm pretending I don't know the answer to. So I have to leave it like that. If I differentiate the left side with respect to x like that, I have to do it to the right side too, just like you do with algebra, where you add the same thing to both sides or whatever, multiply the same thing on both sides. Here we are differentiating both sides. When you differentiate x, you get 1. Now we can just algebraically solve this equation for the unknown derivative. The derivative with respect to x of natural log of x by dividing both sides by that, e to the natural log of x. You could say the answer is 1 over e to the natural log of x. However, that's not as simple as it could be. It simplifies to 1 over x, once again, because e to the natural log of x equals x. Technically, again, all this is true if x is positive. And it really is not a proof of this fact because, again, I'm really implicitly assuming the natural log of x function is differentiable in the first place to come up with this derivation. It's not a proof. Because you'd need to assume differentiability first. You could say it's a proof if we assume or if somehow we know for some other reason that natural log is differentiable. But I haven't really proved that. We're not going to prove it. We're going to be happy with writing that as is. And you don't have to write that middle thing. You can just know the derivative of natural log of x with respect to x is 1 over x. Again, technically, the domain for this is positive values of x because we're not allowed to plug negative numbers into the natural log function. Or 0. Natural log of 0 is undefined. Now, some of you might know a little bit about integrals. And know that if you integrate 1 over x, you get natural log of the absolute value of x plus c. Maybe you've learned that before, a few of you. But I don't see any absolute value signs here. Where is that relevant? What is the natural log of the absolute value of x in the first place? What is that? It's really a piecewise function, because the absolute value function is really a piecewise function. It's ln of x if x is positive. And it's ln of the opposite of x if x is negative. Negative x, which sometimes people say the opposite of x. Because if x is negative, negative x is actually a positive number if x itself is negative, right? Negative of a negative is positive. That's why the word opposite is sometimes used here. So because it's a piecewise function defined over these two different domains that are actually separated by x equals 0, that means we should think about the derivative piecewise as well. If x is positive, it's the derivative of natural log of x, which we've just figured out is 1 over x. And if x is negative, it's the derivative of that, which I need the chain rule for, right? We need the chain rule for this because the inside function is not just an x, it's a negative x. The derivative of the outside function, natural log of x, is 1 over x. So I start writing 1 over x, but I have to plug in the inside function into the x. So I plug in a negative x in place of x, then multiply times the derivative of that inside function. But hey, that's negative 1. So what this means is in the end, you get the same thing either way, 1 over x. Because two negative signs will cancel under multiplication, or you might say under division here. And this is true if x is not 0. As always, you should think about this graphically. Does this make sense? First of all, what does the graph of the natural log of x function look like? You hopefully recall from, second week of class that the graph looks like this. Natural log of x, I'm going to put a little space there. What's the natural log of the absolute value of x? It's also defined when x is negative, and it's got to be an even function. Natural log of negative of the absolute value of x, or I should say the natural log of the absolute value of negative x is the same as the natural log of the absolute value of x, because the absolute value of the opposite of a number is the same as the absolute value of the number itself. Try different numbers. Like if x is 5 or negative 5, this works. You get 5 on both sides. So this is an even function. So the graph to the left of the vertical axis is the reflection across the vertical axis, about like this. So this entire graph together is the graph of natural log of the absolute value of x. Its derivative is 1 over x. When x is positive, that looks like this. When x is negative, that looks like this. That's y equals 1 over x, both when x is positive and when x is negative. I'm not sure if these graphs cross or not offhand. I'd have to double check it. They may or they may not. I'm not positive at the moment. More important thing, though, is to focus on the sign and how big it is. When x is positive, the derivative starts out positive. This is, again, the derivative of natural log of x. And large, just like the slope of the red graph, is positive and large here. The slope of the red graph decreases as x increases. It's a concave down graph, just like the value of its derivative is positive but decreasing. Over here, when x is negative, the slope is always negative of the red graph, just like the value of the blue graph is always negative. And as x gets close to 0, the derivative becomes a large negative number, like negative 1,000 or negative 1,000,000, just like the blue graph goes down forever and ever to large negative values. It's not a proof, but it's good to see that it seems reasonable. Okay, so that's the derivative of natural log of x. How about the derivative of inverse sine of x? We need the fact that the sine of the inverse sine of x, also known as the arcsine function, we could write arcsine of x in there. Sine of x inverse, the inverse function, is not the same as the reciprocal. It's not 1 over sine of x. It's unfortunate that the notation is inconsistent. We just have to live with it. When you mean 1 over sine of x, you would either write sine of x with parentheses and put a -1 outside the parentheses, or you would call it cosecant of x. That's the other name for the reciprocal of sine, 1 over sine. But that's not what this is. This equals x if x is between -1 and 1. Technically, this includes the endpoints here, -1 and 1. However, I'm going to put strict less than signs here because it turns out at the endpoints, the assumption that inverse sine is differentiable actually fails. I'll show you why here in a few minutes. So technically, I'm not going to allow x to be either endpoint here. It turns out then my assumption of differentiability works. And if I differentiate now and use the chain rule, the derivative of sine is cosine. Plug in the inside function, and then take the derivative of the inside function. Don't forget to differentiate the right side as well. That's just an x, so it differentiates to 1. Now do your algebra, divide both sides by cosine of inverse sine. The derivative of inverse sine of x can be written as 1 over cosine of inverse sine of x. However, we don't stop there. Okay, this can be simplified and written as a non-trig function. Again, there are a couple different ways this can be done. What typically people find easiest is to imagine this to be an angle, call it theta. Since you take the cosine and sine and tangent of angles, the inverse sine cosine tangent of a number gives you an angle, or at least can be thought of that way. Draw a right triangle. Label one of the angles theta, one of the non-right angles, it doesn't matter which one. Say to yourself, okay, I know this angle is inverse sine of some number, x. Therefore, the sine of that angle is x, right? Because that angle is inverse sine of x. Sine of theta is sine of inverse sine of x is x. I'm pretending x is a number that I don't care what it is. I'm taking the inverse sine of and getting this angle. Technically, to be an angle written like this, x would have to be positive so that the angle is positive, but let's not worry about negative values. I also know SOHCAHTOA. SOHCAHTOA. So sine is opposite over hypotenuse, this side over this side. I know the ratio of this side to the hypotenuse must be x, because the sine of the angle is x. X is the same as x over 1, so you might as well take this side to be x and this side to be 1. It's not the only possibility. You can make this one be 2x and this one 2. This one be 3x and this one be 3. 4x and 4, 5x and 5. As long as the ratio equals x, it's okay. But it's simplest to choose x and 1. We need to take the cosine of that angle. Cosine is adjacent over hypotenuse. So I've got to figure out the adjacent side. Pythagorean theorem. You could call this side a. You know from the Pythagorean theorem, a squared plus x squared equals 1 squared. So a squared is 1 minus x squared. A itself is the square root of 1 minus x squared. Therefore, the cosine of this angle is the square root of 1 minus x squared over 1. In other words, the square root of 1 minus x squared. And that's what the bottom simplifies to. Now, you might wonder if that's true when x is negative, so that the angle is negative. And I'm not going to go into details, but suffice it to say, this does work when x is negative. This is not the only way this could be derived. We could also use the Pythagorean identity to derive it. Cos squared theta plus sine squared theta equals 1 right away without drawing a triangle, and solve this for cos theta and take the plus square root. we get the same answer on the end. It's a little quicker to use that, actually. You don't have to bother with the triangle. But most people seem to like drawing the triangle. There it is. The derivative of the inverse sine function is a non-trig function. It is a ratio. It's technically not a rational function because of the square root. Rational functions are ratios of polynomials, so this is not technically a rational function, but you could call it a ratio, a fraction, a quotient. Notice it would be undefined if x were plus or minus 1. Now, that's not a proof that inverse sine is not differentiable at the endpoints plus or minus 1, but it's a hint that it might not be. What's going on graphically? The graph of inverse sine, first of all, is the reflection of the sine graph when you restrict its domain across the line y equals x. Maybe I should draw the sine graph in here as well. So here's the sine graph. When x is restricted to negative pi over 2 to positive pi over 2, over that domain, the sine graph is 1-to-1 and has an inverse function. If I draw the line y equals x, so this is the blue graph is y equals sine x, not inverse sine. This red graph is y equals x. The graph of inverse sine, by definition, is the reflection of this blue graph across the red line. It's a little easier if you turn the paper this way, but still tricky. I have a hard time with this myself. Kind of like this is the reflection. Now turn it back the ordinary way. That's going to be the reflection. Since the domain of sine that was restricted is negative pi over 2 to positive pi over 2, the range of the inverse sine goes from negative pi over 2 to positive pi over 2. And since the range of the sine goes from negative 1 to 1, the domain of inverse sine is from negative 1 to 1. Notice at the endpoints of the graph, it's getting pretty close to vertical. And that is true. At these points, if you had to define tangent lines, they would be vertical lines with infinite slope. That's why this function is not differentiable at the endpoints. It's still not a proof, but it's a graphical reason why. And the graph of this derivative, 1 over square root of 1 minus x squared, does have vertical asymptotes at 1 and negative 1. The derivative looks about like this, with vertical asymptotes at 1 and negative 1. That's the graph of y equals 1 over square root of 1 minus x squared. What about the inverse cosine function? What's the derivative of the inverse cosine function? I'm not going to derive it from scratch. Maybe I'll make that an exercise for you to do. Same kind of derivation as here. Technically, the values of x for which it's true is negative 1 to 1, but the actual range of the inverse cosine function is different. Anyway, I'm going to let you know that it is negative 1 over square root of 1 minus x squared. That's interesting. It's the opposite of the derivative of inverse sine. Isn't that weird? Why would that be the case? It is the case. It is true. I would encourage you, if you like math even a little bit, to see if you can figure out why. Maybe I should say, even if you don't like math, not even a little bit, maybe you should see if you can figure out why. Why is the derivative of inverse cosine this? And that's the opposite of the derivative of inverse sine. And in particular, this means something interesting. Something interesting must happen when you add inverse cosine and inverse sine. I'll put question marks, but those question marks are something interesting happens. I'll let you think about that. Something unexpected happens when you add those two functions. Something nice, actually. But I'll let you think about that on your own. Let's do the general inverse case now. f of f inverse of x is equal to x. That's the relationship between a function and its inverse. By the way, this relationship holds even if f is not a very nice function, even if it's not differentiable, even if it's maybe not even continuous. Are there such functions? Yeah. And they can still have inverse functions. Yes, that's true. This kind of relationship still holds. So to take the derivative of both sides, once again, I'm really assuming everything's differentiable. In particular, f and f inverse are differentiable. I won't bother writing that down, but maybe you want to write it to yourself, a little note, assuming differentiability. F is the outside function, f inverse is the inside function. Take the derivative of the outside function, plug in the inside function, multiply times the derivative of the inside function, which we don't yet know. Take the derivative of the right side, that's 1. Now solve for the unknown derivative. The derivative with respect to x of f inverse of x must be 1 over f prime of f inverse of x. And can this be simplified? No, it actually cannot be simplified. This is as simple as it gets. By the way, we could use the prime notation on the left side as well. We could write this as f inverse prime of x if we wanted to. The derivative of an inverse function, assuming it's differentiable at a number x, assuming f itself is differentiable, is the reciprocal of a value of f prime. 1 over f prime of what value? F inverse of x. This is the general form of these examples we've been doing with inverse sine, inverse arctangent, inverse tangent last week, natural log of x. This is the general form of that. Do you ever need the general form? Surprisingly, sometimes yes. Even when you can't find f inverse of x. What's an example of that? Let's say our function y equals f of x is a cubic. Maybe, I don't know, x cubed plus 3x plus 2. And I've purposely made this cubic. I know from experience that the graph of this is going to be 1-to-1. It's not going to go up, then down, then up again. It's going to go up all the time, though it will have an inflection point at, well, some positive value of x. The graph's going to look about like this. This is going to be a y-intercept of 2. And as an example of something I can calculate f of 1, for example, and get 6 to know that when x is 1, y is 6. This is not perfectly to scale. And again, this graph is 1-to-1. It passes the horizontal line test. No horizontal line goes through it more than once. It's invertible. It's got an inverse function whose graph will be the reflection across y equals x. And will look about like this. I'm not turning my paper this time. Oh, this is not the greatest picture. Okay. Oh, that's bad, actually. I could take the time to make a nicer picture. It's not very accurate. Okay, yeah, that's not very accurate. Here's some more inaccuracies. I'm going to pretend this is the point. Well, if this is the point 1, 6, this must be the point 6, 1. And that, yeah, that's a bad scale. Okay, very bad. I'm interested in knowing the slope of the inverse function there. What's f inverse prime of 6? That's a 6 there. Say it one more time. It's a bad drawing. Okay. What's f inverse prime of 6? I got to use this formula. Why? Or how? If I don't know what F inverse is, can I solve this for F inverse? Technically, yes, though if you do it, it's nasty. Well, let's have Mathematica do it. Mathematica do something nasty for us. Mathematica, I want f of x to be x cubed plus 3x plus 2. Same function there. Mathematica, solve, not echoic, bad typing. Solve f of x equals y for x. Solve for the inverse function. What is it? I want to know. What's that? I? That's the imaginary unit. What? Wait a minute. There are 3 answers. And they involve I guess, except for this one. I wonder if that's the one we want. That's the answer? Wait a minute. That's simpler than it looks, doesn't it? Full simplify. 1/6. What? We don't want to solve for the inverse function. Solving cubics is nasty. Can be done. I'm glad Mathematica can do it, but I don't want to do it. But we can still use this formula. F inverse prime of 6. That's 1 over F prime of F inverse of 6. So I guess I need to find F prime. That's not hard. F of x is a polynomial. Cubic. F prime of x is 3x squared plus 3. But what's F inverse of 6? That's actually easy. Do you see it? It's 1. Why? Because f of 1 is 6. So F inverse of 6 is 1. That's why. If the input to f is 1, the output is 6. Therefore, for the inverse function, if the input is 6, the output is 1. You don't need the formula for the inverse function. Oh, and lo and behold, look at this. Magical, 1/6. Oh, I love math. Oh, you already knew that. It worked. Yet the formula for the cubic inverse is nasty. I love Mathematica. That Mathematica did that, and I don't have to. The slope of the original function at this point is 6. That makes geometric sense even. The slope of the inverse function at the reflected point, if I drew it better, would more clearly be 1/6. They're reciprocals of each other. Nice symmetry. Have I put problems like this on tests? I have, yeah. Will there be homework on it? Yeah, I've given homework on problems like this too. You got but it's no harder than what I just did. And you don't have to find F inverse of X. You need to use the fact that F of something is something. Use that fact like I did here. Use this formula that I derived up here. Yes, there's lots of parentheses and stuff all over the place, but if you're careful, you can use it.